हेलो स्टूडेंट्स। आई होप आप सभी अच्छे होंगे और अपनी स्टडीज़ को भी अच्छे से कर रहे होंगे। आज का जो हमारा टॉपिक होने वाला है वो वेक्टर अलजेब्रा होने वाला है। आज के इस सेशन में हम सबसे पहले वेक्टर अलजेब्रा थ्योरी देखेंगे और उस थ्योरी में हम मेनली रिजल्ट्स देखेंगे। ओके, कुछ डेफिनेशंस होंगे, कुछ रिजल्ट्स होंगे। इफ़ टाइम परमिट्स तो हम कुछ एक्सरसाइज, कुछ प्रैक्टिस क्वेश्चंस इस थ्योरीज से रिलेटेड भी करेंगे। ओके, तो बढ़ते हैं आगे। आज के इस लेक्चर में हम क्या-क्या फॉलो करने वाले हैं, आइए देखते हैं। वेक्टर्स एंड स्केलर्स, टाइप्स ऑफ वेक्टर्स, एडिशन, सब्ट्रैक्शन एंड स्केलर मल्टीप्लिकेशन ऑफ वेक्टर्स, इंपॉर्टेंट रिजल्ट्स, एंगुलर बाइसेक्टर्स, पोजीशन वेक्टर, components of a vector in 2D and 3D, vector product or cross product, scalar triple product, tetrahedron and its volume using vectors, vector triple product, and the last one will be linear combination, linear independence and dependence of vectors. Okay, now let me just show you a small disclaimer for our viewers. The images used in our slide deck are just for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@itk.ac.in and we shall remove the images. Thank you. Now let's dive into our subtopics. So first of all, vectors and scalars. So physical quantities are divided into two categories: scalars and vector quantities. Those quantity which have only magnitude and not related to any directions, we call them as scalar quantities or simply scalars. For example, mass, volume, density, temperature, etc. Now for vectors, vectors are those quantities which have both magnitude as well as directions. For example, displacement, velocity, acceleration, momentum, etc. are the examples for vector quantities. A directed line segment is a vector denoted as AP or simply a vector. Okay, so in this case we have initial point as A and terminal point as B. Now magnitude or length of a vector is denoted by modulus of A, which represents what its magnitude or length, and it is always non-negative scalar. Okay. Now types of vectors. A vector whose initial and terminal points coincide is called zero, or null vector is denoted by zero vector. A vector whose magnitude is 1 called as unit vector. A unit vector in directions of A is given by A vector divided by its magnitude, denoted by A hat. Unit vectors parallel to x axis, y axis and z axis are denoted by I hat, j hat and k hat respectively. Vectors are said to be like when they have the same directions and unlike when they have opposite directions. Two vectors A and B are said to be equal if or written as A is equals to B if they have same length as well as same directions. Vectors which are parallel to the same line are called as collinear vectors or parallel vectors. Otherwise, they are called non-collinear vectors. If A and B are two collinear vectors, then A is equals to lambda times B. For some uh, lambda belongs to real number. Vectors having same initial point are called as co-initial vectors. Vectors having same terminal point are called as coterminous vectors. A system of vectors is said to be coplanar if they are parallel to the same plane or lie in the same plane, otherwise they are called non-coplanar vectors. Types of vectors. The vector which has the same magnitude as that of a given vector but opposite in direction called a negative of A, denoted by minus A. A vector having the same direction as that of a given vector A but magnitude equal to the reciprocal of the given vector is called as or known as reciprocal of vector A and denoted by A vector power minus 1. A vector which has drawn parallel to a given vector through a specified point in a space is called localized vector. Vector whose initial points are not specified are called free vectors. When a particle is displaced from a point A to other point B, then the displacement AB is a vector called displacement vector of the particle. Two vectors are called orthogonal if angle between the two is a right angle. Now, addition, subtraction and scalar multiplication of vectors. There are three laws for addition of vectors which are given below. First, triangle law. If a vector A and B lie along two sides of a triangle in consecutive order as shown, as you can see, A vector and B vector, then their sum, or in other term resultant, will be A plus B is represented by the third side, as you can see, A plus B, this resultant, but in opposite direction. Okay. Now parallelogram law. Second, if the vectors lie along two adjacent sides of a parallelogram, so A vector and B vector, as shown in the adjoining figure, then diagonal of a parallelogram through the common vertex represent their sum. So this will be your resultant, or A plus B. Addition, subtraction and scalar multiplication of a vector. The third law, polygon law. If n minus 1 sides of a polygon represents vector a1, a2, a3, as you can see, a1, a2, a3, and so on in consecutive order, then their sum is represented by the nth side, but in opposite, as you can see, this side opposite to the other sides, a1, a2, a3, and so on. Okay, so this will be your what? Resultant vector. If A and B are two vectors, then the subtraction of B from A vector is defined as the vector sum of A and minus B vector. And it is denoted by vector A minus vector B. That is A minus B, which can be rewritten as vector A plus minus vector B. To subtract B from A, we reserve the direction of B and add to it to vector A. Addition, subtraction and scalar multiplication of a vector. Let PQRS be a parallelogram, as you can see, PQRS QRS a parallelogram such that PQ and SR are equal to A, as you can see, parallel to each other and same in length. PS, QR both parallel and same in length, as you can see, B, B. Now, diagonal PR is equals to A plus B, so diagonal PR. So this resultant vector can be rewritten as A vector plus a B vector, and SQ, diagonal SQ, in this way you can rewrite as this resultant as A minus B vector. Okay, we are doing what, as we just seen in the previous slide, this is nothing but A vector plus minus of B vector. We are doing what, reversing the direction of B vector and then adding to A vector. If A is a vector and lambda be a scalar or a real number, then lambda A is a vector whose magnitude is lambda times that of magnitude of A and whose direction is the same as vector A. If lambda is positive, okay, what if lambda is negative? Then your direction will be negative, but magnitude remains the same. So we have lambda A magnitude will be modulus of lambda A product with a magnitude of A. Now, important results. Commutativity holds here. A plus B is equals to B plus A. So, sum of two vectors is commutative. A, and it also holds associativity law. So, A plus B plus C same as A plus B plus C. A minus B is not equals to B minus A. So in this case, it is not equal. Okay. So commutativity not holds here in difference form. Now, magnitude of A plus minus B is always less than equal to magnitude of A plus magnitude of B. Okay. So this is your triangle inequality. Magnitude of A plus B is always greater than magnitude of A minus magnitude of B. Lambda 1 product with lambda 2 A is same as lambda 1 lambda 2 times A, or in other words lambda 2 product with lambda 1 A. Lambda 1 plus lambda 2 product with A vector is same as lambda 1 product with A plus lambda 2 product with A. Lambda product with A plus B is same as lambda A plus lambda B. There is a note. When the sides of a triangle are taken in order, it leads to a zero resultant, meaning in triangle PQR, PQ. So in this, okay, so in triangle PQR, if you have a triangle PQR, PQR, so PQ, QR, and RP vector, adding all them, you will get a zero. Okay, zero vector. Now angular bisectors. Let A and B are unit vectors. Internal bisector of a angle between A and B is along A plus B, and external bisector of angle is along A minus B. If A and B are not unit vectors, then above angle bisectors are along A by magnitude of A plus B by magnitude of E, or in other words, A unit vector, B unit vector. So this is a vector in the direction of B. This is a unit vector in direction of A. Okay, and A by magnitude of A minus B by magnitude of B respectively. So these bisectors are perpendicular to each other. Now position vector. Every point xyz in space associated with a vector whose initial point is 0 origin and terminal point is p. So this vector is called a position vector and given by op, or sometimes mainly represented by r vector. Component form will be x I hat plus y j hat plus z k hat. Using distance formula, the magnitude of OP vector will be what? Root of x square plus y square plus z square. If A and B have position vectors A and B respectively, then AB can be rewritten as a B minus A. And magnitude for AB will be B1 minus A1 square plus B2 minus A2 square plus B3 minus A3 square, then whole root. If A and B are position vector of A and B respectively, and RB position vector of P point P which divides the join of A and B in ratio M ratio N, then you will have R is equals to MB plus minus NA divided by M plus minus N. Here plus sign takes for internal division and minus for external division. If ABC be the position vector of three vertices of triangle ABC and RB position vector of centroid of triangle ABC, then you have A vector plus B vector plus C vector divided by 3. The components of a vector in 2D and 3D. The process of splitting a vector is called resolution of a vector. The parts of the vector obtained after splitting the vectors are known as the components of the vector. Let Ax is the resolved part of A along x-axis, that is the projection of A on x-axis. Similarly, Ay is the resolved part of A along y-axis, means projection of A on y-axis. Then by the parallelogram law, OP, so this OP, this vector is equals to what? ON, so this vector plus NP vector. Okay, or in other words, A, so the OP is A is equals to AX plus AY. So AX I hat plus AY J hat, where AX and where AX and AY are the magnitudes of AX AY. Components of a vector in 2D and 3D. Similarly, in 3 dimension, we can represent vector A as AX plus AY plus AZ is equals to AX I hat plus AY Z hat plus AZ K hat, where AX AY AZ are the magnitude of AX AY AZ respectively. Here AX AY AZ are scalar components of A and AX AY AZ are vector components of A. If two vectors A, B are equal, then their resolved part will also equal, meaning A1 equals to B1, A2 equals to B2, A3 equals to B3. If A is equals to A1 I hat plus A2 J hat plus A3 K hat, and B is equals to B1 I hat plus B2 J hat plus B3 K hat, then A plus B will be A1 plus B1 I hat plus A2 plus B2 J hat plus A3 plus B3 K hat. A minus B will be A1 minus B1 I hat, A2 minus B2 J hat, A3 minus B3 K hat. And lambda times A will be lambda times A1 I hat plus lambda times A2 plus J hat plus lambda times A3 K hat. Scalar or dot product. The scalar product of two vectors A and B is given by A dot B is equals to magnitude of A product with magnitude of B cos theta, where theta belongs to closed interval 0 to pi. Properties of a scalar product is listed below. Commutative law, meaning A dot B is same as B dot A. A dot B is 0, meaning if and only if A is perpendicular to B. A dot A is same as square of the magnitude of A. I dot I, J dot J, K dot K, meaning dot product must be same, which is 1. And I dot J is equals to J dot K, I dot K, J dot I, K dot I, K dot J, meaning equals to 0. You can use this. Fifth, if A is in this form and B is in this form, then A dot B will be A1 B1 plus A2 B2 plus A3 B3. A dot alpha dot B is same as alpha times A dot B, where alpha is your scalar. A dot B plus C can be rewritten as A dot B plus minus A dot C. So distributive law. Scalar or dot product. For any two vectors A, B, we have square of magnitude of A plus B is equals to square of magnitude of A plus square of magnitude of B plus 2 times A dot B. Now, square of A minus B, magnitude of A minus B is same as magnitude of A square plus square of magnitude of B minus 2 times of A dot B. A plus B product with A minus B can be rewritten as square of magnitude of A minus square of magnitude of B. A dot B is negative if and only if AB are inclined at an obtuse angle. A dot B is positive if and only if AB are inclined at an angle acute angle. If A1 I hat plus A2 J hat plus A3 K hat and B vector B1 I hat plus B2 J hat plus B3 K hat are inclined at an angle theta, then cos theta will be what? So this is your dot product A1 B1 plus A2 B2 plus A3 B3, nothing else, and this is your magnitude of A and this is your magnitude of B, product of magnitude of A magnitude of B. Okay, some more points related to scalar dot product. If R is a vector making angles alpha beta gamma with OX OY OZ respectively, as you can see here, okay, alpha is this angle, beta is this angle, and gamma is this angle. Then cos alpha is R dot I, cos beta is R dot J, cos gamma is R dot K, and R vector can be written as R is equals to length of R vector cos alpha I plus length of R vector cos beta J plus length of R vector cos gamma J, where R is a unit vector. If R is a unit vector, if R is a unit vector, then R is equals to cos alpha I plus cos beta j plus cos gamma k, because your in this case magnitude for R will be 1. Now projection of a vector A on another vector B will be what? A dot B divided by magnitude of B. So A vector, okay. So projection of A vector on B vector. So projection on B vector. So your OM, so this will be your projection. So OM, so this is nothing but your dot product A dot B divided by magnitude of B. Component of A vector along and perpendicular to B are OM. So A dot B divided by magnitude of B, as you can see, and MA A minus A dot B divided by magnitude of B dot product with B unit vector. Work done if a particular if a particle acted on by a force F has displacement D, then the work done will be F dot D. Now, vector product or cross product. The vector product of two vectors, A vector and B vector, is given by A cross B, which is equals to magnitude of A, product with magnitude of B, product with sine theta, dot product with n unit vector, where your n hat represents unit vector perpendicular to A and B, such that A, B, and n forms a right-handed system, where theta belongs to closed interval 0 to pi. Okay, and this theta is the angle between A vector and B vector. Now, properties of a cross product. A cross B is equals to minus of B cross A. So it is not commutative. A cross B whole square is equals to square of magnitude of A, product with square of magnitude of B minus A dot B whole square. Third, M times A cross B is same as M times product with A cross B, as you can see, which is further same as A cross M times B. Now, A cross B plus minus C can be written as A cross B plus minus A cross C, and B plus minus C cross A can be written as B cross A plus minus C cross A. A cross B is equals to 0 if and only if A is parallel to B and both are non-zero vectors. If A vector is this and B vector is this, then A cross B is just nothing a determinant for this matrix I, J, K, first row, second row, A1, A2, A3, third row, B1, B2, B3. Now the seventh point, the vector perpendicular to both A and B is given by A cross B. Cross product, some more points. The unit vectors perpendicular to the plane A and B are plus minus A cross B divided by magnitude of A cross B, and a vector of magnitude lambda perpendicular to the plane of A and B or B and A is lambda times A cross B divided by magnitude of A cross B. If I, J, K are three unit vectors along three mutually perpendicular lines, then I cross I, J cross J, and K cross K will be equals to 0. Also, I cross J is equals to K, J cross I is equals to minus K, J cross K is equals to I. K cross J is equals to minus I, K cross I is equals to J, and I cross K is equals to minus J. Now, 10th point, the area of parallelogram with adjacent sides A and B is magnitude of A cross B. Area of quadrilateral with diagonals D1 and D2 is given by half of magnitude of D1 cross D2. So this cross is cross product. The area of triangle with adjacent sides AB is given by half of magnitude of A cross B. If ABC are position vectors of a triangle ABC, then the area will be area is equals to half of magnitude of A cross B plus B cross C plus C cross A. 3 points with position vector A, B, C are collinear if A cross B plus B cross C plus C cross A is equals to a 0. Okay. Now scalar triple product. If ABC are three vectors, then their scalar triple product is defined as the dot product of A and B cross C is denoted by this. Thus, this A B C, this scalar triple product is A dot B cross C. Now properties related to scalar triple product. So as you can see, ABC scalar triple product of BCA, scalar triple product of CAB, all will be equal if they are in this order ABC, ABC, ABC. ABC is equals to minus BAC. As you can see, order here, order breakdown. So CBA minus CBA minus ACB. If lambda is a scalar, then lambda A BC is equals to lambda times triple product of ABC. Triple product of A B C1 C2 is equals to triple product of A B C1 plus triple product of A B C2. A cross B dot C is equals to A dot B cross C. The scalar triple product of three vectors is 0 if any two of them are equal or parallel or collinear. If ABC are coplanar, then triple product of ABC must be 0. Triple product of ABC is equals to 0, then any two of the vectors are parallel or ABC are coplanar or C is equals to alpha times A plus beta times B. 4 points with position vector A, B, C, D will be coplanar if triple product B minus A, C minus A, D minus A 0. Volume of parallelepiped whose coterminous edges are A, B, C is magnitude of triple product of A, B, C. Now scalar triple products. If A vector, B vector and C vector, then the triple product can be rewritten as, in terms of a determinant, the first row will be A1, A2, A3, second row will be B1, B2, B3, third row will be C1, C2, C3. Now triple product of A cross B, B cross C, C cross A will be equals to triple product of A, B, C whole square, which is further equals to determinant of A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C. Triple product of ABC product with triple product of UVW is equals to determinant of A dot U, A dot V, A dot W, B dot U, B dot V, B dot W, C dot U, C dot V, C dot W. If A is this vector, B is this, and C is this vector, then the triple product of A, B, C can be rewritten as determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3 times triple product of LMN. Okay. So if and only if the triple product LMN is equals to 1. Tetrahedron and its volume. A tetrahedron is a three-dimensional figure formed by four triangles as shown in this figure. As you can see, volume of tetrahedron OABC is 1/6 of triple product of ABC. If ABCD are positional vector of vertices A, B, C and D, of a tetrahedron ABCD, then its volume will be 1/6 of triple product of A minus D, B minus D, C minus D. Now vector triple product. If ABC are three vectors, then vectors A cross B cross C and A cross B cross C represent the vector triple product and is given by A cross B cross C is equals to A dot C dot B minus A dot B dot C. Or in other words, A cross B cross C is equals to A dot C dot B minus B dot C dot A. Now properties. A cross B cross C is equals to A cross B cross C. If some or all A, B, C are non-zero or A and C are collinear. A cross B cross A is equals to A cross B cross A, which is further equals to A cross B cross A. Vectors A cross B cross C is perpendicular to A and lies in the plane of BC. A cross B C cross D dot product will be determinant of A dot C A dot D B dot C B dot D. Now linear combination and linear independence and dependence. A vector R is said to be a linear combination of vectors A, B, C, etc. if there exist scalars x, y, z, etc. such that R is equals to xa plus yb plus zc and some other combination. If two non-zero vectors A and B are linearly dependent, then it means there are non-zero scalars alpha and beta such that alpha A plus beta B is equals to 0. A and B are parallel. A and B are collinear. A cross B is equals to 0. Otherwise, A, B are linearly independent. If three non-zero vectors A, B, C are linearly dependent, then it means they are non-zero scalars alpha, beta, gamma such that alpha A plus beta B plus gamma C is equals to 0. A, B, C are parallel to same plane. A, B and C are coplanar. A is equals to alpha 1 B plus alpha 2 C etc. And a triple product ABC is equals to 0. Otherwise, ABC are linearly independent. A set of non-zero vectors A1 to AN is said to be linearly independent if x1 A1 till xn AN is equals to 0 imply x1 to all xn's must be 0 where xi's are scalars. So this is it from the theory side. So we have to end our session. I hope you enjoyed it. Thank you.